Hello dear students, welcome to the lecture series on microelectronics. This is lecture number 29.
Dear students, in today's lecture, we are going to see the open circuit time constants for approximate determination of upper cutoff frequency with respect to the amplifier configuration. Before proceeding further, let's figure out what were the contents that we covered in the previous lecture. In the previous lecture, we try to get the information with respect to the high frequency general considerations that should be taken into account whenever we try to figure out the upper cutoff frequency with respect to MOS amplifiers. And in today's lecture, we are going to move further, and we are going to use a method known as open circuit time constant method in determining the high frequency response of a common source amplifier configuration. Now, once a student understands these or particularly this particular method, then he'll be able to thoroughly solve numericals or thoroughly apply the open circuit time constant method in determining the upper cutoff frequency or higher FH of many MOS amplifier configuration, and thus he can be able to play with the amplifier configurations. Now, today's lecture will fall in the category of level 2, that is understanding the concept of the open circuit time constant method. As we have been continuously discussing about the different levels that are present in the learning hierarchy, we come across the term known as Bloom's taxonomy. So Bloom's taxonomy is a set of 3 hierarchical models used to classify educational learning objectives into different levels of complexity and specificity. Now, under these different levels, today's lecture will fall under the category of level 2, wherein we focus more on understanding the concepts and then we try to summarize the concepts. So, we know that the high frequency response of an amplifier is characterized by a transfer function given by the equation 1, that is fh of s is equal to 1 plus s by omega z and so on upon 1 plus s by omega p1, wherein we have the zeros and poles being represented accordingly. Now let's try to multiply the numerator and denominator. So fh of s can be expressed as as can be seen in the figure 2. I'm just trying to replace all the coefficients related to the frequency of the pole, and also I'm going to replace all the coefficients related to the frequency of the zeros. So I'm trying to replace with A1, A2, A3 and so on, and then with B1, B2, B3 and so on. That's what is my equation number 2. Now in many cases it is not simple matter to determine the poles and zeros. Usually it happens that to determine the poles and zeros and then to identify which is the dominant pole and then figure out that dominant pole's frequency will be the upper cutoff frequency, it takes a lot of manual work. I need to be undergoing or I need to be trying to analyze or determine the poles and zeros using different techniques and then try to determine the dominant poles, and then from that I need to be determining the upper cutoff frequency. But if poles and zeros of an amplifier transfer function are known, then f of h, that is upper cutoff frequency, may be obtained by the techniques presented earlier. Any of one of the techniques can be used to figure out the upper cutoff frequencies if I know the poles and zeros. Otherwise, the following method is used. Now, in many cases, zeros are at higher frequency. So, if that is the case, then it has got a little significance in determining the upper cutoff frequency because my upper cutoff frequency is purely dependent on the poles, and that to the dominant pole. Usually, one of the poles, say omega p1, has much lower frequency than other poles. So, it follows that omega close to midband will occur. So, in that scenario, upper cutoff frequency will be represented as a single static time constant low pass filter network, that is f of h equal to 1 upon 1 plus s by omega p1. So, again here p1, omega p1 is nothing but it is that particular pole which it is the dominant among the whatever the poles we have obtained. So under that scenario, the upper cutoff frequency will be directly equal to whatever the pole frequency I have obtained. If a dominant pole do not exist, then I can determine omega h from a plot of the transfer function or the approximate formula for determining omega h, which we have done in the previous lecture, where omega h is approximately given by 1 upon under root of 1 by omega p1 square plus 1 by omega p2 square, so on, minus 2 upon omega z1 square minus 2 upon omega z2 square, and so on. So we have also seen an example. I'm just trying to recap that example, wherein I have this transfer function. Now I try to determine or try to identify the poles and zeros of the transfer function, and I try to obtain or try to figure out which is the dominant pole. And from the first inspection, I can see that 10⁴ is the that particular pole which is dominant. Hence, my omega h is equal to 10⁴ radians per second. Now this can be even done in a better way, using better estimation, by using the above mentioned formula, wherein I try to substitute different values of poles and zeros. Now the same upper cutoff frequency can even be obtained with an exact value through the help of the transfer function. Now remember, determining the upper cutoff frequency with the help of transfer function is always an optimum solution which gives me an exact value. So that's what we have done in the previous lecture, where we took up this example itself, and we try to obtain the omega h value using the transfer function method. So approximate determination of omega h using open circuit time constant can be taken up in using this particular procedure. Now assuming zeros are not dominant, and we assume that there is only one dominant pole exists, say P1, then this particular equation, so we have this equation number 2. So this equation 2 can be reduced in the form of f of h of s is approximately equal to 1 divided by 1 plus b1s, and even this b1 can be replaced with the help of omega p1. So this is your omega p1. So assuming there is only one dominant pole at omega p1, so this is what the transfer function I am going to get. Now this is helpful for me to approximately determine using the method what is known as open circuit time constant method. Now how do I do it? Now using the equations 4 and 5, I try to obtain the values b1. Now basically b1 is nothing but it is the entity related to pole. So b1 is nothing but 1 upon omega p1, and since there is only one dominant pole that is existing in the circuit, I can say that whatever the frequency of that particular pole is there, the same is the frequency of my amplifier. So that will be my omega h, that will be my upper cutoff frequency of the amplifier circuit. So basically my b1 is nothing but 1 upon omega p1 or 1 upon omega h. Now if there are multiple poles, then b1 will take up value as 1 by omega p1 plus 1 by omega p2, so on so forth. Now if I try to correlate the formula of the b1 with respect to omega h, I can rewrite this entire structure something like this. So omega h can be written as 1 divided by 1 by omega p1 plus 1 by omega p2, so on so forth. Now this omega p1 whatever I am writing, or omega p2 whatever I am writing, is nothing but your RC time constant, which is obtained using open circuit method. Now so basically the agenda here is to find the R values of the entire circuit and the C values of the entire circuit, specifically the R in and C in, and then R out and then C out. When I am going to figure out the R in and R out, I need to be considering all the resistances, even including the R0, and I am going to determine C in and C out. I need to be considering all the capacitance including the parasitics. If I do that, and if I cross multiply the respective input and output RC time constants and try to substitute in this equation, whatever the value I am going to get, that will get me the upper cutoff frequency. Now, in detailed version of how I'm going to do this, we'll deal in the next lecture, wherein I'll take up an example of simple common source amplifier and try to extract the small signal equivalent circuit and then try to build that open circuit time constant methodology using the common source amplifier. I think we're going to get a more clearer picture with respect to the open circuit time constant method when I take up the common source amplifier configuration in the next lecture. So finally I can say that omega h can be represented by 1 upon RC, that is RIO C1 plus R1O C1 plus R2O C2 and so on so forth. O stands for open circuit. Now basically it is nothing but the summation of RC time constants of all the individual R and C's. Now when I try to obtain this particular methodology, there are certain rules I need to be following up. Now rule is that whenever I take up any particular capacitances, I need to be including all the capacitances in the small signal equivalent model, including all the parasitics. Then I will be considering only one capacitance at a time, which means if I consider, if let's say there are 3 capacitances, then if I consider C1 and try to obtain the value with respect to this, then I will be reducing all the other capacitance to 0. So that is, I am going to replace them with an open circuit. And when I do that, I am also going to reduce the input signal to 0 and determine the R input. So basically I am going to make Vs 0 and Is 0 and going to determine the R input. So I am going to repeat all these steps for different values of R and C that are present in the circuit, and then I am going to summate the entire R and C's that I have obtained and obtain the omega h value. Like I said, this entire brief concept will be more clearer in the next lecture, where I am going to take up the common source amplifier circuit itself in determining the upper cutoff frequency using this particular method. So finally, to end up, so this is my upper 3 dB frequency omega h, which is nothing but 1 upon summation of RC time constants, or 1 by B1. Now however, in complex circuit there is a very doubtful of the existence of the dominant pole, and sometimes this particular method is not a preferred choice with respect to complex circuits, but it is a preferred circuit when I am going to analyze with an individual amplifier configurations. So like I was telling, I'll just give you a glimpse of what I'm going to do in the next lecture. So here is what I have taken the common source amplifier configuration, and I am trying to map all the capacitances, that is parasitic capacitances, along with the other capacitances that are discretely available in the circuit. Once I have those capacitances, I try to obtain the high frequency equivalent circuit model, including all those capacitances, and to determine the different, like I was discussing over here, to determine the RC time constants of different capacitances and resistances, I need to be checking, or I need to be choosing the individual capacitances and opening up on the other capacitances, and the same procedure should be repeated for the other capacitance also. Like here, for example, as we all know, FH, or instead of talking in terms of omega h, let me talk in terms of FH. FH is given by 1 upon 2 pi RC. Basically RC is nothing but my tau. Now RC, there are 2 RCs, one RC with respect to GS, one RC with respect to GD. So when I am finding out RGS, I will be considering all these capacitances, and when I am finding RGD, then I will be considering all these resistances. So basically, when I am finding RGS, I will be considering all these resistances. When I am finding out RGD, I will be considering all these resistances. Similarly, when I am talking with respect to capacitances, there are 2 capacitances or 2 major poles over here. One is CGS and other is CGD. When I am talking with respect to CGS, I'll be making it this particular path as an open circuit, and when I am dealing with respect to CGD, I am making this path as an open circuit. So this is how I am going to find tau GS and tau GD, and I make up a summation of all these things, and finally I'll get the total time constant.
So this is how I'm going to determine the upper cutoff frequency, that is FH. which is equal to 1 divided by 2 pi tau, and tau will be the total time constant of all the resistances and the capacitance present in the entire circuit. Now to summarize, now today's lecture we understood the importance of determining the upper cutoff frequency using an unique technique known as open circuit time constant method, and this method can be used to determine the any amplifier's upper cutoff frequency with very easiness. So it includes whenever we determine any upper cutoff frequency of any amplifier configuration, since I need to be including the overall resistances and the capacitance that are present in the entire amplifier configuration. So this method is very well suited for the determination of upper cutoff frequency. So this is it from today's lecture. Hope you have enjoyed the today's lecture. Thank you for the patience listening.